Good morning, everyone, and welcome once again to the JKMRC Friday Seminar series. So on behalf of the University of Queensland, we'd first like to acknowledge the traditional owners of the land on which we meet today and pay our respects to their ancestors and descendants who continue cultural and spiritual connections to country. It's my great pleasure today to welcome Dean David. So Dean was with JKTech for 8 years from 1996 to 2003 and was manager of consulting for the last half of that time. Dean graduated with a Bachelor of Applied Science in Metallurgy from SAIT, which is now the University of South Australia, in 1981 and worked with CRA and Rio Tinto at Broken Hill on the WIM150 Mineral Sands project and at Argyle Diamonds for over 14 years. Dean left JKTech to become process manager at then GRD Minproc in Perth. 20 years later, Dean still works with the same process team in Perth, but now under the banner of Wood, which is a global multi-market engineering company. So please join me in welcoming Dean for his presentation this morning.
Thank you, Daniel. And to do the traditional thing and start with a safety share. If you've seen my publicity picture, you'll realise it's fairly old. So never believe a publicity picture put in front of you. I think that's 15 years ago. It was the one I could find as quick as possible. But yes, I've grown a little bit older than when that picture was taken not that long after I joined the people in Perth at Minproc. It's good to be back at the JK, although sitting a long way away in Perth, and presenting rerunning a presentation that I made at Minerals Engineering Comminution 23 conference a few months back in Cape Town. What I'm talking about this morning is vertical roller mills versus ag ball circuits. And I've been designing and dealing with ag ball circuits ever since joining JK back in '96, and doing a lot of that through the years with Minproc and its successors through to what is now Wood. So the idea of going into a new technology is always one that's very slow in our business, and the vertical roller mill presents itself as a technology that's somewhat new to our business, but very old. In fact, it's nearly 100 years old in its current form, and it's used in the cement business, coal business, and many others that we sort of sit on the fringes of, and is now pushing its way into the hard rock minerals business. And for those of you that know, the VRM has been selected for the West Musgrave nickel copper project, and in remote Western Australia. And it was an Oz Minerals project, but it is now a BHP project after the acquisition. Excuse me. If you can look at the picture that's on the screen, the VRM is the big green thing, and that's built by a group called Lersha. We'll talk about them in a minute. You can see the people down the bottom of it. So this unit is very, very large and quite imposing. Most of it is air, and there's a classifier at the top, but we'll go through that later as well. The other picture is the cyano-iron ag mill installation, which is topical because it's a magnetite project we're talking about, and cyano-iron is magnetite, and it's the biggest ag mill magnetite project globally, with 6 of these 28 megawatt mills. Right. Just to acknowledge the other people who contributed into this paper, there's myself, there's Dr. Carsten Gerald, who works for Lersha, and Christian Smith, who also works for Lersha. These the guys have been instrumental in the development of the technology and development of the testing for the technology. Stefan Barkin also for Lersha, and he has been involved very strongly in making this technology forge its way into the minerals area. Sorry, Deanne Olwagan from Grange, Chris Stanton and Michael Everett are from Grange Resources, who own the Southdown deposit, and are basically the client in this situation. And I'm obviously from Wood, and we've been the engineer that's been directing how this progresses over the years since about 2010. So who are Grange Resources? They have the Savage River magnetite operation in Tasmania, which commenced way back in 1966. It is pretty much as it was designed. It's an ag ball mill circuit. They get 45% of what they mine into a concentrate, a very high grade magnetite concentrate, and they make 2.5 million tonnes per annum of that. And then they pump it north to the coast to a pellet plant. And you can see some of the pictures here. We have the ag mills on the far right, sorry. In fact, if we go below that, we're back in the mine, and we've got the primary crusher and a conveyor coming up to where the mill sits on top of the surrounding country. And this is fairly close to the actual Savage River, which flows through the pit. And once the concentrate is made, and after ag milling and ball milling and mag separation, it goes to pelletizing. And those pellets then go into a furnace and get fired. They then get stacked and they're ready for sale. And these are about 66% iron and a premium product. Once they've gone through the firing, they've been converted to hematite. And just a bit of a story about why there's a good connection here between myself, or JK Wood, and the Savage River operation and Grange in general. Sorry. Australian Bulk Minerals acquired Savage River in 1996. And then they came to JK and they asked for someone to come and have a look at their mills and their magnetic separators and see if they were useful to continue on, because they were going to bulldoze the whole plant. So I'd just come from Argyle. I've been using mag separators there, and Rob Morrison sent me down to have a look at what they were doing. At that stage, my exposure to sag milling was pretty low, but it was getting better. And ABM restarted their operations in 1997. And then we were back very soon surveying the plant, mainly because it wasn't behaving as it was thought it would, because we were told it shut down because of hard ore, and the ore they started mining on was very, very, very soft. I think we measured about a 600% recirculating load of pebbles. So there was a few things to do with that circuit to get it going. We did find the hard ore, but it was nowhere near where they were planning to mine for about 5 years. And we then had an ongoing relationship with Grange, and we looked at various milling issues and product quality issues. And Minproc was already working with Savage River on a recycle crushing project, amongst others. And obviously I wasn't with them at the time. But then I joined Minproc, and the jobs moved from more of rather than surveying through to more engineering over the following years, through to about 2007 and 8. And that's when the Southdown project started to come onto the scene, and we did a major review in 2009, 10, and basically took over the project. So what is Southdown? It's in Western Australia. It's a big magnetite deposit. And at the moment, we've got a plant designed for 5 million tonnes per annum of magnetite concentrate, and it's sitting in basically farmland in Western Australia. And the other player is Leurscher. Leurscher originated in 1906 in Germany, and they were always have sold grinding gear. And they released the first mill of the Leurscher, what we now know as a Leurscher type, in 1927. But ones before that were similar, but they then improved it. And they were pretty successful. 400 mills were sold in 10 years. And then over the next 4 decades, ramped up the capacity of the units to something like 1,500 tonnes an hour maximum now. That was basically in the last 4 decades. So they've had 100 years of in-house comminution development and devotion to the business of grinding. And they've had their own pilot facility, which has an extensive database. And you can see here, they've done more than 10,000 grinding tests. They've got 17,500 data sets of industrial performance from the machines they have sold. And those are linked together with these grinding tests. So they have grinding, they've got verification of what their grinding tests were telling them. They've now sold more than 2,300 of these mills, and they're up to date with basically a lot of things in terms of research and going forward as well. And I believe they're involved in projects that the SMI JK are also involved in. Who are we as Wood? We do consulting, feasibility, engineering, and construction, and getting projects up and running, ready for the project. So and we were Minproc, but now with Wood, it's 160 years of history. Apparently, we got about 40,000 people based in Aberdeen. There's a whole lot of mining offices around the world. A lot of them were old Minproc offices, and we have around about 500 staff in Australia. And we work on all sorts of jobs, and my main job is in the study area and the consulting area, rather than the actual details of getting something built. And that's just a quick global map of what we do and where we do it. So that's where Southdown is. There's Albany, and there's Perth up here. That's about 300 or 400 kilometres, 350, I think. And that's about 90 kilometres by road from Albany. So others were involved in the work before 2009. We did the review. We did the ag and ball mill laboratory work, and then pilot plant testing at what is ALS in Perth. We also then issued a feasibility study based on ag milling and ball milling. And that project sort of bounced around a bit, having some difficulty with getting approval. Also, during that time between 2012 and 2020, the market wasn't all that good for iron ore. Then things picked up, and the interest was back. There was a desire to reduce things like water and other things. So we looked at some dry processing options for it. And out of that, we recommended that because we were doing work with Leurscher already on other projects, that we do some testing at Leurscher on their ore. We did some open circuit test work with their standard machines, and we prepared a PFS, pre-feasibility study for the installation of these mills for the project in 2022. Just after that, in 2022, we conducted closed circuit pilot testing of vertical roller mills. and that was sort of impacted by COVID and various other things, and meant it wasn't ready to do before we issued the pre-feas. So the pre-feas was based on what we thought might happen in a closed circuit operation, and we'll talk about that later. Lersha actually built a facility for closed circuit testing of this material, and I'll tell you what that means soon. And then we did the tests to actually find out what happens, because it was almost impossible to do any prediction as to what would occur in closed circuit versus open. And a feasibility study is being done at the moment by others, not by Wood. And there should be some results of that coming out soon. This is the picture of the ore. As you can see, it's pretty chunky. This is 150 millimeter core, which we drilled so that we had some big material to go into the ag mill. It's very coarse grained. And all the core is like this. There is no sections of core that are shattered or anything else. It's all just solid like this. Drop weight indices 5 to 6. And the ball mill work indexes were about 18 kilowatt hours per tonne. And it was probably the most consistent material I've seen, with everything being in a very narrow range from 17 to 20 kilowatt hours per tonne. So there's no soft stuff to find here. Fairly abrasive. SG is reasonably high due to the high magnetite content. And that's around about 35 to 37% magnetics, but that includes pyrrhotite. And that's not nice for the concentrate. So this percent sulfur number is important, because you have to get rid of it, have to get down to 0.05 before it's useful, or else you make sulfur dioxide in pelletizing, and you destroy the pelletizing plant. This is various times that samples were taken and tested. And as you can see, there's reasonable consistency across the time frames there. And we found that because of the competence of the ore, we can have this sitting in a shed down at site for 10 years, and it was still behaving in a similar fashion to when we first drilled it. The deposit is very long, 12 or so kilometres, and the first part of it is 6 kilometres. The reason they stopped there is the highway from Albany to Esperance crosses that deposit about there. And you can see where we took the drilling across down the length of that deposit. And that was just drilling for the pilot plant. This is a bit of discussion about what we want to do when we are trying to upgrade a magnetite deposit. If we come to the top here of this diagram, you'll see there's 100 millimeters up here. So this is effectively the ore as it's in core, or as it's in the ground when you mine it, and fairly low grade magnetics as you can see by this color, which isn't black, whereas it's very black down here. And this represents the amount of free silica that you could get rid of if you were doing a separation at that size. And as you come down further and further, you get down to something like the mass of magnetite available to you at about pure magnetite grade, because pure magnetite 72.4% iron. In fact, with this material, they can get pretty close to 70.0% iron in the final concentrate. And if you stop at any point along here, there's the magnetite grade in what is the valuable component of the ore increases, and the amount of liberated waste that you could get rid of. The grade increases of magnetite, but the proportion of mass decreases, because the proportion of mass that you could get rid of is increasing all the time as you get finer and finer down here. So down the bottom, you can, for example, grind it all the way from ore to 40 microns, and you should be able to make a separation immediately of a final grade concentrate. But you've now ground the total 100% of the mass, whereas the idea is to actually do this progressively. So if we take little slices at various sizes, you might have 90% of material that will respond magnetically because it's got some magnetite in it, and only 10% that you could throw away without losing anything. You crush it a bit more, you might get rid of 20%. So we would typically not do a separation if you could only throw away 10% of the mass. 20% is getting sensible, and you need to know what size that is. So for every ore, these sizes are different, and these liberation characteristics are different. And basically, once you've thrown away a bit of material, the next stage has less to deal with, and less again for the next stage, less again for the final stage. And basically, you're getting closer and closer to pure magnetite as you go down these various stages. And the trick with design is finding out what these are, what sizes are sensible to use in this sort of progression. And you'll find most magnetite deposits have at least 2, and sometimes 3, and sometimes 4 stages of grinding and then magnetic separation. So for Southdown, what we're going to look at here is taking the ore from feed size to about 150 microns, minus 150, which gives you something in the range of 85 to 125 micron P80. And we're going to look to do that with a single separation stage. And that is what we did in the pilot plant for the SAG mill or AG mill circuit and ball mill circuit. So the task for both milling options we're looking at is to grind it, as I said, to 85 microns and to reject non-mags on the way through. If you don't do that, we can't actually compare properly to the ag circuit option, and you'll see why in a minute. So let's start with our conventional grinding pilot plant that we set up in about 2011, 10 and 11. In the pilot plant, we prepared the feed to minus 150 millimeters, and I simulated up a size distribution in JKSim that we tried to match by various crushing exercises on the material, and we got reasonably close. Of course, in industry, primary crushers generate materials that are minus 300, and we did have some material that was a core that was 150 millimeters diameter and maybe up to 200 millimeters long, but anything bigger wouldn't fit through the feed chute of the pilot ag mill. We can do ag milling, and we did it with and without pebble crushing. In the design, we're looking at ag milling without pebble crushing. Due to the limitations of pumping and various other things in the pilot plant, we screen the product at 1 millimeter coming out of the ag mill. In the industrial situation, we're going to go for a 3 millimeter screen because the rougher magnetic separators can handle that size of feed. Again, we would do RMS on minus 1 millimeter, whereas in reality, it's a rougher magnetic separation on minus 3 millimeters. Ball mill is the same. We ran a ball mill, but we classified again with screens, 150 micron screens in the pilot plant, but in reality, it would happen with cyclones. So there's a whole lot of things different in industrial operation than we actually would have done in the pilot testing. And what actually happened in that? Well, as you can see in the top right here, we've got very nice media in the ag mill, very nice rounded ore. And here's one bit of core that's obviously been in there a very short time because it's still most of its original shape, but everything else is nicely rounded pebbles. They were disappearing pretty fast, and it was quite an efficient milling exercise. And here you can see the difference between the non-mag stream and the mag stream in that circuit. And that's the pilot ag mill. And basically, we measured all the power in the system for both the ag mill and then the ball mill circuit afterwards. And we achieved 103 microns, not 85, and it took 19 kilowatt hours per tonne across those two circuits, and that's per tonne of new feed. And in this non-mag separation, almost 40% of the feed was rejected before you go to the next stage. Now, what that looks like in an operation is you would have an ag mill and a ball mill, which is a fairly common arrangement, except we have 3mm screens in the system, and everything coarser than 3mm goes back around and comes back to the ag mill. Everything finer goes to magnetic separation, and only the magnetics are put into the ball milling circuit. And we finished up with 22 megawatt ag mill and about a 19 megawatt ball mill in that design. And it's not uncommon for the ag mill and the ball mill to be pretty much the same size, given that we've got rid of 40% of the mass in these magnetic separators. So what are the advantages of doing wet milling? It's pretty safe because everybody knows how to do it and design it. Well, some people do. There's enough people out there to do it. So the easy bits about it is you only have to primary crush before an ag mill. It's an established process. There's few effects on flotation downstream to worry about, especially in the piloting side of things. And you've got quite a high throughput per line, up to a few thousand tonnes per hour if you need it. The challenges are that the pilot settings don't match. Pilot settings and the pilot effects are not what you expect to see in operation. Screening your ball mill circuit is totally different to cycloning your ball mill circuit product. It's a fairly complex flow path, and you have to test that properly. Reasonably high power consumption. And you also produce quite a lot of wet tailings out of that circuit because, of course, ag milling, as we know it these days, is done wet. And these days, wet tailings are not a good thing because you've got to filter them. So let's look at what a VRM circuit does. In the pilot plant, you prepare it to minus 16mm just for the size of the gear. In the industrial, all you need to do is secondary crush the ore, and you can do that in open circuit because you can achieve a minus 100mm size. Some places, some softer ores would handle 125mm top size straight into a VRM. We looking at grit extraction, and I'll explain what that is. We could eventually achieve grit extraction in a pilot situation exactly the same as would happen in practice. You need to use dry Gauss, dry high Gauss RMS, rougher magnetic separation on those grits to reject a coarse fraction. And basically you can emulate that at pilot scale. You return the grits that are magnetic to the VRM to be ground further. Again, the same can be done at pilot scale. And the product that is generated is exactly the same because it's generated by air classification, both at pilot scale and at full scale. And because of the database they have, that's been proven many, many, many times. So what was the pilot VRM like? The comminution specific energy, remember we had nearly 20 kilowatt hours per tonne for the ag circuit. The comminution specific energy for this circuit was only 4.5 kilowatt hours per tonne, which is pretty spectacular. And that's from 16mm to 83 microns as we achieved in the test. And that could be controlled very quickly by their automatic systems, which are controlling this closed circuit pilot plant. However, that looks like a very nice number, but half the industrial power, well, firstly, it needs to be scaled up a bit for coarse feeds, and then you have to add on the power of the fan in the system, which is almost the same as the power, even more sometimes than the power used for comminution. So the specific energy coming out of the pilot plant has been estimated at about 11.3 kilowatt hours per tonne. and the rejection of -1 millimeter rougher mag separation non-mags, which you can see down in this picture. There's your mags, there's your grit non-mags, was 41% of the feed mass. And that again is a pretty realistic number that can be achieved at full scale, depending on how you set the machine up. You can see these magnetics here, quite granular from what we call the grit, and the final product is obviously very fine and powdery magnetics, or quite high in magnetics. Here is the pilot flow sheet. The feed comes in and it goes down on this flat bit here represents the grinding table, and that rotates with a shaft which drives it in the center from below. These are rollers that are pressed down onto the grinding table. The ore gets ground between the grinding table and these rollers. The rollers aren't driven at all. They're only forced with the hydraulic pressure downwards, and they turn as a result of the grinding table and the ore that sits between them. Material comes off the edge of this table, is raised up through the machine with an upflow of air. There's an air classification system up here. Anything that meets final grind size goes through the classifier and comes into a baghouse where it was captured as final product, which is this material here. The grit material is the classifier course, and it normally would fall down here and return to the middle of the grinding table, work its way out, get ground, and have another pass. In this circuit, most or all of it can be taken out outside the machine, put over a magnetic separator. You throw away the waste and you return the magnetics. So you would throw this fraction away and you return this fraction, which is about 80% magnetite, back into the feed. And what happens is basically 6 + 8 equals the feed mass of 1. So more you can throw away here, the less material you have to grind all the way to 85 microns. And that's where one of the major benefits comes from. But this sort of benefit of throwing away a non-mag also happens in the SAG circuit or the AG circuit. So it's not the main thing. The main benefits actually come from the grinding, efficient use of energy in the grinding process. So in terms of VRM milling, what's the comparison for advantages and challenges? You can put a big size of particle in, and you can go a couple of orders of magnitude down in terms of particle size and produce that product in one step. In fact, this machine could take 85 millimeters and make a 20 micron product. The classification is integrated into the system, and it's designed by the same people who designed the grinding circuit. And it's got 100 years of development sitting in it. And almost all of what happens in the pilot plant is equivalent to what happens in the industrial circuit, which means the product you get out of this, you can actually test with confidence in the downstream circuit. You've got this high energy efficiency, and you know that in today's parlance, it's renewable ready because you've got a lower energy requirement. So a given size of solar installation or wind installation becomes more useful in a greater proportion of the required power. No water required at all from feed to product. It's totally sealed. There is no dust in a system like this. Some of these plants are the cleanest I've seen on the inside. And typically they ramp up in a few weeks because they have done this everywhere with many, many different operations. Obviously, moving into a new area like hard rock, they've had some slow ramp ups in their initial areas where they've tested this, but they've learned all sorts of things in that process. And I call that the bleeding edge of technology. And I went through that with HPGRs at Argyle Diamonds. The challenges are that if you're not careful, the flotation effects can be a problem during testing, as we did find out. There are wear effects present for abrasive ores. You've got high-speed air moving things around, moving what is effectively a grinding powder around the place, sandblasting. You have to deal with the grits once you get them out and put them into a separation system. And that requires conveyors and mag separators and various other bits of gear that are now dry. And you have some size limitations at the moment of 1,500 tonnes an hour. In fact, for this particular circuit, it's about 900 to 1,000 tonnes an hour of South Down ore to be processed through a single large VRM. Just a word on the flotation effects. We did a test on the VRM. We sent the product, we sent this material through to another lab for float testing and mag separation downstream. And it performed terribly it's got pyrrhotite in it. So pyrrhotite floats pretty well, but it floated disastrously in those tests. Fortunately, a few months later, another test was done. And immediately it was done, we were able to grab some of this material, put it under nitrogen, get it to the laboratory, do its first mag separation, and then do a lab float test immediately. Very similar to what would happen in an operation. It would come out of the VRM and be straight into mag separation, then flotation. The response was the best we'd seen for any test ever on this material. And it was very clean float, very fast float. And we got down to levels of sulfur that were 0.02 against a target of 0.05. So you can really stuff up the downstream work if you don't treat the product out of a VRM with some respect in terms of its ability to oxidize sulfides. This is one of the early designs. It's not the current design that we put together, and basically the feed would be crushed off to the right at the pit and in a primary and secondary crusher. Then it would come through into the VRM system, and this is the product baghouse. There's a coarse recycle coming back, and also, sorry, that's the, yeah, there's a couple of recycles. One of them is coming, yes, I'll get it right now. This is the fine recycle, which comes and feeds the mag separators. You then have a non-mag product, which is rejected, and a magnetic product, which returns into the system. In fact, it goes this way and returns to the feed conveyor. This stream is a coarse stream from the bottom of the machine with particles from 5 millimeters upwards, which is also recycled back to the feed. And that's a feature of every VRM unit. And here we have a 17 megawatt unit and another 17, and each of them doing 950 tonnes an hour. So what's the comparison? The VRM, 12.3 kilowatt hours per tonne versus 20 in wet milling. So that's a 41% benefit. The non-mags are 35% rejected versus 32. That's a 9% benefit. The water consumption had a 24% benefit to the VRM circuit. And tailings disposal could all go to a dry stack without filtration, whereas the tails are wet from the wet milling, and you would have to filter and do various things to get them into a tailings arrangement. So conclusions. The VRM grinding only requires 60% of the energy as we measured with these two pilot arrangements treating exactly the same ore. And you can have 76% of the water consumption of a conventional wet grinding circuit in this environment. You obviously can't get these sort of water consumption reductions if you're not rejecting a dry non-mag. So a lot of grinding circuits like the one at West Musgrave won't have a grit rejection system. They'll be grinding 100% of the material down to their final grind size, and they won't have the same water benefits. And the pilot test work for the VRM is much simpler, standardized, and it requires much less mass than ag milling. And then once you've done the pilot testing, you've got a huge database of information to work with. Most of the guesswork is taken out of the scale up, well, all of the guesswork. I found there was an excellent team technically working for this group, and they know their comminution, they know their stuff. So from my perspective, it was a pleasure to do this bit of the work and to be for them to actually put the money into doing a closed circuit system, which they had never done before, and cost them a few $100,000 to actually implement. So we now strongly recommend VRM technology for the Grange South Down project, and we've been evaluating the technology for 6 to 7 years, and it's provided similar benefits to other clients. So the outcome of all that for us is that we'll be offering this as a standard comminution alternative in situations where it's actually suited to the ore that we're dealing with. And it will be up against HPGR, SAG, AG circuits as a viable alternative for which we can very quickly get a test performed. And as I've said, Oz Minerals is putting this together at the moment, or BHP is putting it together for the West Musgrave project. And that's the presentations. I'll put it back to you, Daniel.
All right, thank you, Dean. That was a really interesting presentation. So I'll now open the floor up to questions. So if you're in the lecture theatre here, you can just raise your hand, or if you're online, you can either type your questions into the Q&A box, or you can raise your hand and then I can unmute you and you can ask it directly to Dean. So we have an online question from Malcolm. So did you consider pebble milling in the ag circuit as per Scandinavian practice?
Yes, we did, and we did some pebble milling test work, and we did some pebble milling calculations. I think it is suitable for pebble milling. In fact, we did recommend it to the client. The problem was that as soon as you go to pebble milling, you halve the SG of your media, and you double the size of the physical mill shell that you have to install. So instead of 1 ag and 1 ball mill, you have to go to 1 ag and 2 ball mills. And they were very capital sensitive, so they weren't very keen to take the operating cost benefits. And those benefits were nowhere near 40%, but they were certainly worth taking.
Hi, Dean. Tom here. Look,
Tom.
You mentioned that you had flotation recovery issues on sulfide with some of this process, and I know that you say that the West Musgrave project is going to be using it for their nickel, which I presume is all sulfide hosted out there.
Yes.
So is it the oxidation? Is it that fundamentally that it's a dry process producing very fine particles that you get a lot of surface oxidation that messes with the flotation performance?
Yes, but it only happens in the test work. So it's a time-based issue, and we had the 85 micron material sitting in bulker bags for 2 months before being further tested, and that's too long. And we had no protection on it like nitrogen or anything else. And I think even if I've seen the same effect with dry ball milling in test work, where people have saved some time by dry milling a sample the night before and then starting the test with that dried material even after being in the fridge the next day, and the results are disastrous for a reactive sulfide or even a low to medium reaction sulfide.
So is that because I haven't seen? I mean, I'm a geo. I don't really know much about this side of the processing world, but I haven't
feel
seen.
for you. I feel for you. Yeah.
I haven't seen. Well, look, there's one of the benefits. I come and sit onto these talks where I look at the title of the talk and go, I don't think there's going to be anything in there that's interesting to me, and then I come and sit through the talk and go, oh wow, this is fantastic. But so ignorance is a blessing here. But the yeah, I haven't seen these mills operating in too many base metal mines, for example.
They don't. No.
And is that the reason fundamentally, or is it
No,
just
no. It's
tradition?
It's more tradition. These have always been focused on softer materials, and the tradition is that you know, that they can't be put into service in hard rock applications. Whereas there's a lot of these that are treating slag, crushed slag from blast furnaces and things like that. So there's quite a lot of fairly abrasive, difficult materials that are currently being treated by this, but it's basically out of sight, out of mind in terms of the hard rock business. But they did have some hard learnings in the Palabora phosphate application, and they had some wear issues and all sorts of things which they solved over time. But they were there the whole time fixing it and making sure that they could actually offer something that would survive in the hard rock industry. And of course, a lot of the cement applications and coal applications, they get away with fairly small machines. But we in this business, we want the biggest and the best. So you know, even 1,000 ton an hour machine is seen as being limited in a lot of the current projects.
And sorry, not at risk of hogging the mic here, and this might be a completely stupid question, but would it be possible to use water or another fluid instead of air as the medium that moves the particles around here? Like, could you have a sealed wet system where, you know, you could maybe integrate it with flotation or something along those lines to operate?
I believe there is work being done in that area. I'm not familiar with it, but I believe they are looking at similar things. Obviously, in an environment where you don't want to use water, that it's something you don't necessarily want to do. But in this business, there are advantages typically of almost everything that every option you have is applicable in some situation. So there are people looking at that at the moment. I'm not sure if it's Lurcher or a Lurcher is assisting that.
Well, thanks very much.
That's all
right. We have another online question. So from Kim Rungy. Thanks for the presentation, Dean.
Hi, Kim.
Do you know of any comparison in the liberation per size produced between conventional and VRM grinding?
We haven't done the exact measurements. However, given that the grits that we produce are coarser than the non-mags we produce from a similar grind size in the ag circuit, and the grits have no fines in them, but you can get rid of 41% of the mass of the feed compared to 32% of a non-mag with fines in it. To me, it says, yes, this is working just like an HPGR would in a selective liberation case. So there is a whole lot of non-mag, for example, in the sub 75 micron region in this machine that could also be rejected in the, but the grits do not contain anything minus 75. Whereas in the ag circuit, most of the grits, most of the non-mags you produce are minus 75 microns. So there is quite a big difference in the size of rejection that you're achieving and the massive rejection you're achieving. So I think the effects are very clear from when you stand back and look at it. And I think if you got closer and looked very closely, I think you would find massive benefits. And I think it's this particular ore that is suited to this process, because it's a very coarse-grained material, and you've got very clear distinction between the magnetite materials and the non-magnetic materials at course sizes.
All right, we have another online question from Craig Brown. What infrastructure is required for maintenance activities, and are there specialist maintenance skills required for VRMs?
Okay, there's two main, if you like, big wear items, which is the table itself, and also the rollers. Now, the rollers are in an arrangement where they actually rotate through about I think it's 120 degrees or thereabouts from their operating position to a sitting on their back position pointing to the sky outside of the unit itself. So they just rotate up like that. They're outside the unit. You then unbolt and it can be lifted off. And all the lifting arrangement is built into the actual gear to get those units off and to put a refurbished or new roller on to replace it. The table itself is about 120 tons of casting. It's the thing that takes the longest to get made, the biggest component of the whole lot, and but all the wear components are removable. So it's a removable flat or circular bed, if you like, around the outside of the table itself or near the outside edge. So, and typically they do these sort of changes either a couple of times a year for something like Southdown, but once every few years for their typical applications.
All right, and we have another online question. So this one from Rob Stevens. Iron ore is very abrasive due to the hard silica. How have you assessed the impact of abrasive wear on the grinding surfaces for the VRMs? What is the estimated lifetimes for the grinding surfaces? I think you've just partially answered.
That's right. That's right. The numbers came out reasonably high. Interestingly, the operating costs in terms of wear replacement, the maintenance costs are slightly higher for the VRM. So you're not going to save on sort of liner costs for SAG and SAG, AG, or ball milling, especially with an abrasive material like this. But they do test that. They weigh materials before and after their standard test to work out how much mass was lost. In fact, they do their tests with mild steel components just so that they can wear out enough to measure sensibly the actual performance. And with this material, we did find that the 16mm top size was a little bit of a worry, and there was some obvious damage from some of the biggest particles. And that's why they've lowered the top size. I think it's now been lowered to 85mm from 120mm, which they first recommended. So there are learnings that have come out of the test work that say, yes, this is going to be more difficult than their typical feed.
Okay, and then another question, this time from Kristen Brook. Is Lersch's experience growing on how hard rock abrasive materials affect the wear rate of the mill components? Are they improving their mills for this specific sort of duty?
Yes, they're looking at all the time at the wear patterns inside the units, and obviously with the high airflows that are going on, you get erosive wear up through the system and into the various passages that take the ground material and the grits. They're looking at most of the inside of these sorts of machines are now aligned with ceramics, and they're looking at the best way to have those ceramics arranged, and also how to avoid things like turbulence, which actually cause some of those wear patterns. So, but they have lots and lots of things operating out there, so they see these issues all the time, and they're in a continual state of improvement with the wear issues. They know that this is their major challenge in moving into this part of the business.
Okay, and a question from Rod Ventura. Thanks for the presentation, Dean. Any rough comparison on CapEx/OpEx on the same throughput capacity?
Yeah, the CapEx has been looking reasonably similar, maybe higher for the VRM. So the OpEx, as I said, the maintenance side of it's similar or even greater for the VRM. It's the power OpEx which is down significantly, and also the water consumption in this case is down as well. The the other thing is because you've actually removed more waste as a result of this this machine, you then finish up with smaller downstream equipment as well. So it has effects beyond itself. So it's not quite as it's not quite genuine comparing direct capex for capex for the grinding job itself. You have to look at the overall capex. So there are some reductions. There's also the ability, for example, to get rid of a stockpile and come straight from the mine through primary, secondary crushing and feed this thing at 900 tonnes an hour. And that, if you can do that, you can get rid of a stockpile quite a lot. You're not really also limited to some of the restrictions in crushing that you normally see with the ag and SAG mill circuits. You can have the primary crusher a bit coarser, and just make sure the secondary crusher in open circuit achieves the top size that you're trying to chase. And if you can get rid of a big stockpile, that's quite a few million, 20 or 30, 20 million or so that you can take out of a grinding line.
All right. Well, there's no more open questions from online. So that's it. I might thank you, Dean, for giving your presentation today. That was really good. Thank you.
My pleasure.
So next week we'll have a special session of the seminars, which will be dedicated to Albin Lynch. So Albin's son Martin will be speaking on the day, and then we'll have a special morning tea afterwards. So we hope you can join us for that. Thank you, everyone.